We feel today our mission is really to demonstrate that we can deliver a cost-effective, engineering, sound solution to your problem. And as we were going through this process, it's very easy to get caught up in the technical side of a structural defect in a building. And we realize there are some intangible aspects to this. There's the technical side, there's a business side, and there's also, in this case, there's an interesting public relations side. So the technical side is pretty clear. We have to supply you with a structurally sound, meeting code building that has a 50-year life. Not maintenance-free. I don't think you're going to want the carpets for 50 years or the paint, but generally a structure you can count on will function for 50 years. On the business side, we understand that you're trying to restore basically a one-stop shop scenario for your county citizens. You're trying to restore a transportation center, and you're trying to get back, maybe there's some inefficiencies or costs that are getting created by being in multiple scenarios rather than that nice building you had before. On the real soft side, the public relations side, we're here to assist you in making a decision, whether it's to go ahead and repair the building or take another, whatever your other alternate routes are. And we've tried to walk in your shoes, and we realize that at this point, that you can't have 90% confidence or 95% confidence, even 100. You have to have 110% confidence to move forward with a process of this nature. It's the 11th hour, and there are no room for bad experiences. So we're going to go through a process here of, we're going to talk about very briefly. I know in our proposal we went through all the people's resumes here. We don't want to stand and beat on our chest, but we're going to go through the companies who's represented here briefly, the individuals, just as things that relate to what they bring to the table here. But more importantly, we want to go through how we're going to operate as a team. We have multiple companies here. We'd like to understand what are the roles and responsibilities, lines of authority, and how we produce a seamless project using a team like this, and how we've done in the past. We started out, after the RFP went out, looking at, well, we started before that, but physically on site. We wanted to get a handle on the forensic side of what's going on in the building. And specifically to get a handle on, do we agree with what's been found on a couple key items in testing of the building or evaluation? And we want to tell you what we found, what was consistent, what wasn't in that process. And then we'll present our life safety and serviceability remediation program. We also want to just take a couple minutes and have you understand this is a construction process, and we want you to understand our culture, how we run a project of this nature in an operating facility. And of course, we're going to talk a little bit at the end about schedule and cost of closing remarks. So to start out, Structural Preservation Systems will be basically acting as the general contractor and contract holder in this process. We are recognized as the industry's leader in this business in the strengthening and repair concrete structures based on the fact that we have done 15,000 projects in the repair and restoration. And in the design-build world, we have been trusted with structures on design-build teams on structures like the Guggenheim, Falling Water, the Supreme Court, IMF, the New World Trade Center, and some structures that aren't so marquee like you see there on the right, that refinery in Texas. That ugly-looking structure makes $1 million a day. And people put their trust in us to literally hold that structure up. It weighs 2 million pounds and take the beams out from under it and put it back together while they're online so they can keep operating. And we have a history of doing these things out of town and linking up with local other businesses like you see sitting here. And we're about a $400 million financially strong, very capable company from a capability point of view. WDP represents one of the industry leaders in the evaluation and repair of post-tension structures and building facades. They've done over 700 projects, and they also have some very good expertise in forensics, which is very valuable in this process. You probably all know Bill Pease from BMGP. Bill Pease has been, his company's been operating since 1925, as well as Carlton Veit, who is also a local company here in the architectural world since 1951 and has been involved in a couple of notable projects here. Dahlke Construction, which is actually the oldest family-owned construction company in the state here, has done about 1,000 projects in 90 years. They will be acting, and I'll go through some of the details, but they are basically acting as a local contractor to work with us through some contract arenas. And we've also connected with MEP Consultants EESI, who actually did the MEP analysis for you. We felt they would be a great fit to deal with some of those issues as they know the building pretty well. One aspect we find is when we go out of town like this and we do these type of jobs, there's a lot of local flavor and spirit that is helped by having local people with you. There's also a lot of things that can be done by local carpenters and local workers and local businesses that are way more efficient than us shipping people into town and doing things like that. So this is a pretty typical process for us. BMPG will act as a key part of this, and we typically do this when we go out of town. BMPG brings us local support of, for one, I'm going to show you our design process, and basically they're going to peer review everything we do. We're not putting them in a position of trying to figure out specialty engineering, but once it gets to calculations and things like that, it gets a little simpler for an experienced company like BMPG to peer review our stuff, as well as they're very experienced in how the local building officials work here, how the process is here, and we instantly dial into an educated system to go through that, which is, in a restoration, is not an easy process. This is a restoration project, and I will guarantee you there are changes and unforeseen conditions, and we want an experienced engineer set of eyes that's within minutes of the job site, not having, you know, get someone in here a day, or we have one of the WDP guys who would like some. We want to be able to connect Bill Pease and the engineer record that I'll introduce to you in a second, to be able to communicate and work things out and just have somebody local. It's just more cost effective and keeps the process going. Carlson Veit will do architectural work in this process, more on the building envelope also, but mostly there's a lot of things that we're doing that could affect ingress, egress, parking issues, fire, leads rating. For example, we're going to show you, we're going to be doing a larging of concrete elements in the building. We have to be very careful about space and ingress and egress. There's things we're doing to the fire system because we have to move it out of the way. We have to make sure they go back in the right manner and things like that. And then there's also some architectural things with finishes they'll support us on. And EESI basically is going to help with the commissioning and renovations of some of the things they've already told you about. We'll handle the structural will handle all the heavy lifting with the strengthening aspect. We'll be bringing people out here that have the specialty construction experience to do that. However, a good portion of this job is local carpentry and labor support. A lot of this job is finishes and MEP related, and they're going to come on board, and Rich's group is going to basically manage that level of subcontractors for us, and they'll also do all the finish work for us. You had asked for some interrelationship matrix forms. Just about all the things we submitted to you between WDP were our key items. There's jobs up there that are of the size of this project and of the complexity of this project that we've had a long history of working with them. And one thing that's interesting, the jobs, the numbers we gave you of those projects, the dollar value, are pure strengthening and remediation. They're not $100,000 of strengthening work on a $5 million restoration of a building. It's all strengthening work. Just some quick notes. Dr. Randall Poston is a gentleman who literally is one of the go-to guys in this industry in any type of post-tension issues and structures. He's been in the business about 31 years, and I know this may not mean anything to you if you're not in the concrete business, but he's the chair of ACI 318. That is the worldwide Bible for how you design reinforced concrete. He's the Peyton Manning of that world. He's okay? He's Peyton okay? All right. Also at WDP, who's going to be a structural engineer, is Dr. Keith Kessner. Where are you? I'm going to move over here. And he's a official on a committee kind of related to what we're doing because it's the committee that defines all the repair methods and means that happen in the engineering world for repair. And Eric Peterson with WDP has been in 19 years in this business, focused just on building envelope work. He's actually the chair of the society that deals with existing masonry structures and the repair of them. And I'm not going to go through their years, but you can see up there, you got a couple years up there of service and a lot of jobs. Dr. Akradaji works with structural. He is past chair of ICI 440, which is the design guideline worldwide that was developed to how you install FRP and how you do the design. And he's been in this business for about 18 years. I also am part of that committee, and I've got about 30 years experience in this business and been involved in about 1,000 projects very similar to this. So to start with the forensic thing, what did we find and what was consistent with what? Our goal really was just to get a feel for, there was some conflicting information over time, and I will say, you had a lot of reports done in the last few years, and we wanted to get a handle on what was up. Some of them were consistent, some of them weren't, but I will tell you, it wasn't money bad spent. It allowed us, because the volume of testing, and we tested consistent areas where they did, it allowed us to understand what was consistent and to move on to the next to look thing. So they were actually very valuable to us in the process. The other thing is we want to understand what the true effect on a structure is. When you do forensics on an existing structure, especially when there's a defect involved, you can't just look at the lab notes. You basically got to figure out what's going on globally with the structure. Has it affected something as extreme as the load-bearing capability, or is a long-term durability issue? Is the problem stabilized? Does it grow worse every day? Are there outward signs that are consistent with, wow, I found this in the lab, and you go to the structure, I should see certain outward signs of that sticking out? And then, as I mentioned, how much testing do you? How do you do it? Where do you come to your conclusions? So what we've done in the last couple months is we've done some visible observations, we've done concrete core samples, we've done ground penetrating and surface penetrating radar, which looks into the structure, and we can see the reinforcing. We've done fiberscope, which is a fancy little microscope. You can make it look around back side of corner and inside holes and things like that. We took a lot of wallboard out and looked behind it, and we also checked some elevation issues by checking regarding this deflection thing. So I'm going to go through one, just give you a brief, but I'm going to spend a little bit of time on the first couple because they've been issues that have really been in your mind. You've been told things about them. They've made the paper, and the first is the strength of the concrete in the structure, which was designed as a 5,000 psi structure. We sampled the same locations on every floor where you had a test before, so we had some cross-reference. We tested this cores for not only compressive strength, but also for tensile strength. And I'll tell you why that is important in a minute. We found that the results were consistent with what you've been told. There's some that are above, some are below, but they averaged out to about 4,300 psi. So there's been numbers anywhere between 4,000 and 4,300. So it's pretty close to each other. So the concept here is the concrete strength is what it is. So what you do is you use that number, you use the in-place number, and you reevaluate what the structure does, and you model it with that. It's not deadly that the concrete's a couple thousand psi lower. You just have to figure out what the effect is. And you model that, and you see what it does. And since we're strengthening it, we can take that real existing capacity and work up from there. So it's really not a deadly issue. Matter of fact, all our modeling, we took a very conservative approach. We only used 3,500 psi in our design, and we're still able to meet the criteria to upgrade the structure. So, and we'll go, as we're going through the project, if we're this, we would actually do more testing just to make sure that 3,500 is okay. And if it's not, we would adjust. The other issue that really has been a hot potato is the micro-cracking in the concrete, which has been described as micro-cracking. It's been described as the aggregate is disbonding from the cement paste. And if you look down at concrete, concrete is a couple things. Concrete's basically 75% aggregate, little sand to big stone, and it's glued together with a cement paste, which is about 25% of it. And when it cures, it looks like a big dense material, but it's really not. It's just a big hard sponge. And what we found in our petrographic review of this was that the cracking, there's two types of cracking in the concrete. The first one was cracking that started in the concrete and it went around every piece of aggregate. Now, why is that important? What does that mean? Because you say, hey, it's micro-cracking, and you jump to the conclusion it's disbonding. When the concrete cures and becomes this big hard sponge, it's so cohesive that when you have problems, especially these, they call them delayed deleterious phenomena. We put that in our report because it sounds pretty interesting. But it's basically an event that's happening and these micro-crackings happening. Something's going on in the concrete to create this cracking. But once the concrete is mended together, those cracks will literally go right through the aggregate. It's acting like one piece. All the micro-cracking that we saw and all the other reports, it goes around there. So what that tells us is that cracking happened very soon after the concrete was placed. And it tells us that it's not a long-term process. It was something that happened, some type of stress, whatever it was, that basically happened before this mended up. And you typically do not see that turn into a long-term problem. So the other type of cracking we saw was drying shrinkage cracking. Now, drying shrinkage cracking occurs, if you look at the petrographic cross-section, it occurs very close to the top of the surface. And the reason concrete shrinks is when you pour concrete, you put all this excess water in there so you can make it flow, and that water evaporates. So to give you a perspective, if I poured a 40-foot piece of concrete, it will shrink 1/3 of an inch with a good water-cement ratio. Now, in all the reports you've probably seen, you might have heard, the water-cement ratio is kind of high on your concrete. So imagine more water has to come off, right? It's going to shrink more. And if that slab is restrained by the columns, which it is, at that water-cement ratio, you would expect to see some minor micro drying shrinkage cracks. And they occur at the top. They do not go down through the section. So in conclusion, we do not feel in any way, shape, or form that micro cracking affects the integrity of this concrete, long-term or short-term. And we base that on having 2 petrographers look at that. There's no outward signs of distress, which if that was debonding, you'd be seeing some type of distress. And the real kicker for us was testing the tensile strength of the concrete. If there's disbonding between the aggregate and that cement paste, and you try to pull that concrete apart in tension, the numbers are super low versus what they'd be. And all the testing we had, they were typical numbers. They showed no, and those numbers were well within the area of normal concrete at this compressive strength. So we do not feel that's an issue at all. Another issue I think that's got a little more legs, I think I read in a blog or in one of the comments in the newspaper last week about someone said they could see the deflection from outside the building. This building's 12 years old, and there's 2 types of deflection. The minute the concrete cures and you pull the shoring out, there's short-term deflection. It's the load, the weight of the structure, no matter what you do, especially you've got monstrous spans. 38-foot span on that outside bay is unheard of. With the type of construction that was selected. You would never do that if you know what you're doing. And there's a way we can calculate what's acceptable. It's going to deflect. You can't stop it. By Oregon code, actually the number that's allowable is pretty simple. You take the span in inches, you divide it by 240, and it tells you what that center deflection should be. Given that, we went around the building and we tested a lot of areas, especially the areas that were showing on that dramatic-looking colored graph that you've seen with the deflection. And actually, our numbers concurred with that. But we also found that only 5%, we're thinking a max 10% of what we checked of the slabs in that building by square foot actually have any deflection that do not meet that L over 240. And if they do, our plan, as we'll show you later, is to level them out. And then on the building envelope, we found some interesting things. We agreed with what Sarah came up with. There were a little bit more water leakage situations going on in various parts of the building. We had the luxury, by dumb luck, of being in the building in your January monsoons, which the wind and amount of rain is probably more than what Eric does when he goes out and does a water test on a building. So we pulled a lot of drywall off, and we were really able to see what was going on. And we'll explain some of the details of what we found. The roof membrane looks to be in good condition, needs a couple minor repairs, but the exterior masonry, and I'll explain why in a second, has been displaced so much that in multiple occasions, notably at the 5th floor and the corners. I'm going to start going through some of our life safety repairs, what we found in the process, and then I'm going to go through the 3 structures, and then we'll go back to the serviceability. But before I do that, you've probably seen this, there's 2 specific repairs the bulk of what we're talking about here will fall into. One is taking this carbon fiber material and basically adhering it to a structure or wrapping it around a column. When you have to go beyond that, now you're into a different technique. It's basically section enlargement. It's a very fancy word for we're going to add reinforcing steel and concrete to the structure, and we're going to make a slab thicker or a column bigger or a beam deeper. And in order to do that, the tricky part is it's not like placing concrete, because at the end of the day, these 2 materials have to act compositely. So you can see the process starting here. It's a process where you have to really roughen the concrete, and then we form it up and we pump our material in there, nothing exotic, until we get it filled, and that's where it changes. Now we have to pressurize that form, because I described concrete as a hard sponge. Our mission is to get that new material, which is a custom mix we use, very flowable mix. We're going to literally pump it and pressurize it so it goes into the pores of your existing structure so they're one piece. If they do not become one piece, or composite's the word, basically you've added some dead load to the structure, it does nothing. So that technique is a pretty specialized technique in this process. The other issue with the slab, and you've heard about this probably ad nauseum, but is related to the amount of post-tensioning in that structure, and the forces in there have shrunk the slabs. And you've probably heard the term elastic shortening or shrinkage. What we found was very consistent with SARE report, but we have a different conclusion of what some of the results we're going to do are. When you put 350 to 500 psi, which is way more than you would ever do on a normal structure, but we understand what the engineer was trying to do. There were such long spans, they had put so much post-tension force to keep that long base span at the edge of the building supported, they had to do that. Now, what happens is when you have that structure under that tension or compression for so long, it shrinks. And you can calculate what that shrinkage is over time. But there is no real code that says you can't put 300 to 500 psi. What it says is, if you put 300 to 500 psi in there, you better account for the stress or the relief of that as that building wants to move. Because if you lock it up, you're going to have all kinds of problems. And basically, that's what's happened to your facade. Now, elastic shortening has happened. You probably have had 90% of that happen. We've calculated what it is. We've compared it to the SARE measurements. They count. So that shortening, that force is all, it's basically shrunken. It is what it is now. It's not going to change anymore. What's interesting is, when this is from the SARE report, is if you look at the second floor, third floor, as you went up the building, that elastic shortening got more and more and more and more. It could have been related to the concrete quality or stressing, but at the top floor, at this roof, the shortening was much less. And the only thing we could come up with out of the old reports was they added a chemical admixture to the roof slab that reduced the shrinkage. It was a shrinkage compensating admixture. So maybe that, or maybe there's less PT, but for whatever reason, doesn't matter, the difference between where that shrunk and this shrunk is the biggest in the building, which is why there's a major problem with the facade at the top of the building. It's trying to pull it in, and it can't. And believe it or not, your building uses studs to hold that masonry system in place. It's a very flexible system. Some people like it, some people don't. But if they had used something more stout, you'd have had a major problem. Luckily, it was flexible enough to move to where it did. It probably would have been much worse if it was a different type of facade. The other things with the slab you've heard is this punching shear. You've got a situation where, kind of like my pen in this paper, is the slab's trying to punch through. And it's a pretty dramatic failure. What we selected was drop panels. We are going to enlarge the bottom of the concrete, and the size of that depends on how big the span of the column is supporting. We're going to, as I described before, roughen the surface, add reinforcing steel. We're going to pump in to that void overhead. We're going to pressurize it so we drive the concrete into the pores, and you end up with a nice piece of concrete in the structure, fireproof, looks like the rest of it, and it solves your punching shear problem. Another thing we found was there's some column issues that were reported in the SARE report. On the first floor, you've got these very high, 16-foot slender meaning the width to the dimension of that column is a little bit thin for what it should be. And the concern is not the axial load. The concern, it's so slender, it could buckle. So they were not identified in the other report. And then in 2 to 5, just about every column has a problem with axial force and bending. And unfortunately, the percentage it has, we cannot just wrap carbon fiber around it. It will not meet code. So here's just a quick graphic of what we'll do. That's the original column. We'll roughen the surface. We put the steel around it. We form and pump and fill it up. And now the concrete drop panel makes even more sense versus the steel, even if you could use it, is we can pump one material up through this whole thing and fix that in one shot. So we've got a drop panel and then a large column. Here's a case study. We just recently did this. This is an office building where you can see the reinforcing steel, then the formwork, and we'll pump that up. The other issue in the building is the bending capacity of the slab in the office building and the bending between the columns, basically how it's bending in the middle. So we're talking about having to do something on the bottom side of the slab between the columns to strengthen it. There's an existing amount of steel, and then we obviously can't put steel back in the concrete. So what we're going to do and proposing is to put an equivalent amount of carbon fiber on the bottom side of the slab in those areas to be equal to that steel. And it would look like this. We would glue it on the bottom in one direction or two, depending on the design. As we get down to the garage, there were, in the SARA report and others, some deficiencies in the footings, basically the foundations that the columns sit on all the way down in the basement, and they would be fixed by using this technique. Some of the columns have to be strengthened already. What we do is we cut out the slab, and this red indicates how we would enlarge that footing to strengthen it and be able to take the loads it requires. And it looks like this. This is a project we did recently in a parking garage. We open the slab, we thicken the footing, and we pour the column. That was the original size. You can see the one that's fixed back here. Then the other thing that has been looked at in the building is the lateral support. It's the building moving as a whole building right to north, south, east, west, during a seismic event or during wind or things like that. And the things that keep that building strong doing that basically are your west core, your stair tower, and your east core. They stiffen the building. Only the west core was shown to be deficient, which was noted before. We found the same numbers that Sarah found. And if you look at here's the stair tower, look at that in cross-section. What we found was some of the walls were deficient in shear, basically. That's why you see those cracks in them, in shear, and they're less than a 15% deficiency. We can actually glue the carbon fiber on them. The ones that were above 15%, we actually have to enlarge. So if you looked at that process, that's a shear wall, and we're gluing horizontal pieces of the carbon fiber on it. And if the other ones were actually would roughen the surface and bump out the wall and make it thicker. So this comes into play where Carlson Vite's we're going to have to work very closely on. We're in ingress-egress areas that have very tight tolerances for that purpose. So we'll have to design these things that they are thick enough or thin enough to meet that criteria. Let's shift over to the transit wall, which is a 10-inch slab with a brick paver system on it. Some forensic work was done, and they note that the membrane that's underneath on the deck below the pavers was probably not the right type of membrane. It was basically too soft. The protection board that was under there was not done correctly, so it allowed it to slide around. The sand that was used was not the appropriate sand. The slab also has excessive, compared to normal construction, pre-compression in it. It's got an awful lot of post-tension force. However, again, like in the building, there's a lot of punching shear deficiency in that, and that's probably what saved you with all that compression in there. So it really doesn't create any life safety issue as far as having that high pre-compression. The bottom steel, which is the steel made for bending between columns, is deficient. They found that was also found in a SARA report. These red lines represent how deficient it was, and the carbon fiber up there shows how we calculated fixing it with carbon fiber. On the top side of the transit wall is a little trickier. There's as much as half the amount of steel in there that should be in there for bending. If it wasn't for that high level of pre-compression, you probably had a problem. So the challenge is it's such a high level of deficiency that you can't just put carbon fiber on top. What we propose to do is use a bonded overlay, and that bonded overlay is going to kill a few birds. I'll explain. For one, we're going to bond a concrete surface on the top by taking the pavers out. We've now got a nice void there to fill up, and we're going to bond a bonded overlay in there that's going to have all the steel that's required in that overlay. It'll be a nice, dense material that'll act as a reinforcing system. It'll also act as a wear surface for driving on. The other thing that in the garage we found was there's also punching shear deficiencies. Same like the building. Now, the challenge with this is the deficiency in punching shear is so high that if you put a drop panel in, punching shear is a function of depth. To put a drop panel in there, it has to be so deep that you would completely foul up your clearance in the garage. So what do you do? Well, what we came up with was we designed this overlay to not only be an overlay for the bending and a wear course, we designed it such that we can put a much more shallow drop panel in there because we combine the same two systems. So that top surface is acting as multiple scenarios as well as a new drainage system. It's helping with the punching shear. Otherwise, you got a problem with height clearance. So we have to come up with a way which is, and we're removing a paver system that's probably going to be problematic to you for a long time. We also found some columns in the garage that were deficient. We found them to be deficient in axial capacity, but their level of deficiency is such that all we got to do is go wrap some carbon fiber around them. Won't take up much space. We paint them. Very innocuous. Just to switch over to the north block, one of the questions that came back to us was related to what did you design your repair for the north block? And frankly, there's not enough information that we could glean to what the load or capacity or demand is on that, because I'm not sure what you're going to put on it. I don't think it's ever been determined. So we picked 100 pounds per square foot in our design. That would cover for you if you ever put vehicles on top of it, or if there was ever a gathering area there, or made it a plaza deck. That would be appropriate load. What we had suggested at this point in time was either if you could supply that to us, we could comment and do an analysis on it, or if you're ever going to develop that, you could save that analysis for the engineer record of that project. In general, it also has punching shear issues. I've showed you what we're doing, so I won't go through it in detail. And it also has some issues in it that we're going to have to put carbon fiber on the bottom of the slab for bending. Now, if you've ever seen anybody work on a building facade, you'll either see suspended hanging scaffold going up and down on a motorized system, or you'll see a system that's mounted on the ground that takes these guys up on what looks like a big long elevator. We may be using both depending on where we are in the building, but in all cases, our proposal includes building sidewalk, safety sidewalk bridging to have people be able to access 360 degrees around the bus mall versus shutting that down. This is something typically you would see. We put lights under it. Sometimes it's a bit wider, but we have it built in our proposal to do that so you can keep street access around the building. On the top surface of the bus mall, I'd mentioned we're putting this bonded overlay on, and because of the nature of the traffic and for additional waterproofing, we're going to put a system on that's called a low mod epoxy. It's an epoxy system that you put an epoxy down, you broadcast different type of aggregates in it. And you can feel this if you want. It could be very aggressive, it could be lightly aggressive, there's different color aggregates that can be put in, but this is probably the toughest wear system you can put on concrete. We've put this on projects, hundreds of thousands of square feet on LaGuardia runway. The planes land and take off on this. And they did a 15-year study of what systems, and this is what they went with. We just finished a project at Union Station, the train station in Washington, D.C. They also have a bus mall. And basically, you can see this is a sample for. It's that color. You can see the system down. So when we put that bonded overlay down, we'll create a very tight waterproof system. This will be kind of the belts and suspenders and wear coat that will get you many, many years of wear on that surface. And that's included in our bid. I will applaud you for thinking out of the box. You've had a lot of different attacks you've taken at this, and I think by making the move, by bringing and soliciting design build specialists from this arena is something that at least has pushed this thing over the goal line, because now you have a complete full package where you've got these jobs are as much about construction as they are about engineering. And when you package that up, you get a complete answer and you can make an informed decision. And I applaud you, because as a public entity, you don't see that too often. You usually don't have the ability to do that or dance around it, and I hope it was worth your while. We very much appreciate you allowing us to bid and be participating in this meeting. We are very, very comfortable that, oh, I got a typo up there, a safe, structurally safe, double safe. I think by note of the questions you asked us today from a technical point of view on our document we submit, that we've done a lot of due diligence here. We're very, very comfortable with the evaluation, the existing capacity structure, and what it really needs to be. we think we've given you a cost-effective option to not only get it functional, but freshen the building too. When you go back in there, it's not going to feel like the day you left and just dust it off. And lastly, you got a pretty hard decision, and I use the term the 110%. I will tell you that if you go forward this and you select this team based on our past history, I hate to sound cliche-ish, but we have been there, done that many, many times, and you will be 100% happy that you picked a contractor and an engineering team like this. This is something we do day in, day out, and we will deliver what you need. So again, I don't think we have any more questions. I will thank you all very much, appreciate your time, and hope to hear from you soon.